Have you ever witnessed the sky ablaze with lightning during a volcanic eruption? Welcome to the electrifying world of volcanic lightning. This rare spectacle is more than just a visual marvel. It's a complex interaction between the eruptive force of volcanoes and the atmospheric conditions above them. When a volcano erupts, it spews ash, dust, and gases high into the sky, setting the stage for these dramatic electrical displays. Stay until the end of the video to discover how these magnificent light shows can tell us more about the mysteries of our planet. But how does a thunderstorm begin to form in a volcano's ash cloud? Let's delve into the fascinating interplay between volcanic eruptions and thunderstorm formation. Typically, a thunderstorm starts when warm, moist air rises and cools to form clouds, leading to precipitation. In the unique scenario of a volcanic eruption, this process takes an electrifying twist. As the volcano erupts, it spews not only lava, but also copious amounts of ash into the atmosphere. This ash, composed of tiny, jagged particles, plays a crucial role in thunderstorm formation. Imagine these ash particles as the ice crystals typically found in regular thunderstorms. They collide with each other within the turbulent ash cloud, and through these collisions, static charges begin to accumulate. This accumulation is not just a random event. The intense heat from the volcano enhances the rising of superheated air, which further elevates the ash particles. As they rise and collide, the environment becomes ripe for electrical charges to build, setting the stage for a spectacular electrical display. Keep watching to find out how these charges build up to create one of nature's most dramatic spectacles. The buildup of electrical charges is a story of separation and excitement. Within the chaotic environment of a volcanic eruption, a fascinating process unfolds as tiny ash particles are thrust into the air. These particles are not just simple specks of dust. They are charged with the potential to create one of nature's most spectacular displays: volcanic lightning. As the plume rises, ash particles begin to collide with each other with great force. It's during these collisions that electrons, those subatomic particles that orbit the nucleus of an atom, are forcefully knocked free. This action creates a separation of charges. The lighter, positively charged particles tend to rise towards the top of the plume, while the heavier, negatively charged particles remain closer to the base of the volcano. This segregation of charges builds up a tremendous amount of electrical tension within the plume. Friction further amplifies this charging process, much like rubbing a balloon on your hair. The result is an electric field so strong that it can no longer be contained. Stay tuned, as next, we'll witness the climactic moment these tensions finally snap. And now, the main event: the spectacular discharge of volcanic lightning. Imagine the scene: towering clouds of ash rising from a volcanic eruption charged with energy. As these clouds ascend, they carry with them various particles, including ash, ice, and rock fragments, all whirling in a chaotic dance. In this tempestuous environment, particles collide and generate static electricity. Over time, different regions within the cloud accumulate varying charges. Typically, the lighter ice particles gain a positive charge and rise to the top, while the heavier ash and rock particles bear a negative charge, sinking lower. The stage is set for nature's grand spectacle when the electrical potential between these positively and negatively charged areas intensifies. The air, a natural insulator, eventually can no longer contain this building tension. With a dramatic flare, the accumulated electrical energy surges through the cloud, seeking a path to resolve this imbalance. This results in a brilliant flash of volcanic lightning, a powerful and awe-inspiring display of nature's electricity. But what does this mean for the surrounding environment? Stay until the end to find out. Not all volcanic lightning is created equal. In the tempestuous world of volcanic eruptions, lightning can form in awe-inspiring ways, each unique to its specific environment within the ash cloud. Let's delve into the two primary types: near-vent lightning and plume lightning. Near-vent lightning, as the name suggests, occurs close to the volcano's vent. It's almost theatrical in nature, with lightning bolts crackling through the dark, gritty plumes of ash right above the erupting vent. This phenomenon typically happens when the eruption column is most vigorous, hurling particles into the air that collide and generate static charges. On the other hand, plume lightning tends to occur higher up and further away within the volcanic ash cloud. This type extends out into the expansive ash plume that can drift miles into the atmosphere. The particles within the plume continue to collide and charge electrostatically, creating spectacular lightning bolts that can be seen streaking across the sky from great distances. Up next, we'll explore how scientists use these fiery signals to study volcanoes. Volcanic lightning is not just a stunning spectacle, it's a window into the volcano's soul. As plumes of ash and dust collide and charge within a volcanic cloud, they create dramatic displays of natural electricity. But beyond its visual majesty, this phenomenon serves as a crucial tool for volcanologists. By observing and measuring the characteristics of volcanic lightning, scientists can deduce a wealth of information about the ongoing eruption. The frequency and intensity of these electrical discharges can indicate the size of the eruption. More lightning suggests a larger, more powerful eruption, as it implies a greater amount of ash being thrust into the atmosphere. Moreover, the height of the lightning within the ash cloud helps researchers estimate the plume's altitude, an essential factor in determining the ash's potential impact on nearby communities and air travel. The analysis of particle size within the ash is also refined through these observations. Smaller particles tend to carry more static charge, thus enhancing the lightning activity. This research not only deepens our understanding of volcanic behavior, but also significantly improves eruption forecasts, thus enhancing public safety. So the next time you see a photograph or video of volcanic lightning, remember, it's not just a light show, it's science at work. In our final segment, we'll summarize why understanding and witnessing volcanic lightning is crucial. As we have seen, volcanic lightning is much more than just a light show. It's a fascinating interplay of nature's most volatile elements, combining fire, earth, and the raw power of electricity. Throughout this exploration, we've unraveled the mystery of how thunderstorms can form within the turbulent ash clouds spewed by erupting volcanoes. We began by understanding the birth of these unique thunderstorms, triggered by the intense heat and rapid ascent of volcanic ash. This ash, filled with particles and gases, creates the perfect nursery for electrical charges to develop. As these charged particles separate, with lighter positively charged particles rising and heavier, negatively charged particles falling, a dramatic charge imbalance is created. This buildup of electrical tension seeks resolution in the form of volcanic lightning, a spectacular and violent discharge that lights up the ash cloud in breathtaking flashes. These are not your everyday lightning strikes. They are born from chaos and serve as stark reminders of our planet's dynamic nature. We also delved into the different types of volcanic lightning, such as near-vent lightning, which occurs right at the volcano's mouth, and plume lightning, which dances high above the ash column. Each type provides unique insights into the electrical and physical properties of volcanic plumes. The scientific significance of these phenomena cannot be overstated. By studying volcanic lightning, researchers can gain invaluable information about eruption dynamics, helping to improve prediction models and safety measures for populations living near volcanoes. Thank you for staying until the end. Remember, the next time you see a volcanic lightning, you're witnessing one of Earth's most powerful demonstrations of natural electrical power.